In this video, we're going to be looking at differentiability and continuity. So as a preliminary reminder, let's look at this graph here where we're taking some function f of x, y, and what we do is we're making a linear approximation of that function at the point A, comma, B. And to get at the idea of differentiability, let us first think about the idea of error. So when we talk about error, what we mean is how well our linear approximation, so creating a plane, how well our linear approximation can approximate the actual function at a point that is close to our point about which we created the linear approximation. So let me say that again. We created a linear approximation around the point A, comma, B. Then what we can do is we can say, well, what if we add h to A and k to B, and that brings us to a new point? How well does my line approximate, or not my line, but my plane, how well does my plane approximate my curve? And what we do is we can think about how well it approximates it in terms of its error. So this error is the difference between the actual value, so f of a plus h b plus k, that's my actual value, minus my approximation. And ideally, what we want to do is we want to make our error to be really, really small. So the idea of differentiability is that provided that this error gets close to 0 as h and k get close to 0, we say that the function is differentiable, or in other words, that we can approximate it with a plane. So here's some formal language, but worth going through. So it says the function is differentiable if we have some linear function. That's the L of x, y. That's our plane up here. And we know how to find the equation for that plane. So here it is written again, such that the error is defined here. Now, they have it written slightly differently than I did, but notice that this is the same thing, that our error equals f minus L, which is exactly what we had on the last page. Just going back one. So here our error f minus L. So our relative error, now here's where we're bringing in our error divided by the distance that the point is away. And that's called our relative error. So as long as our relative error gets close to 0, then our function is differentiable. So let's think about that. As h and k are huge, as they get really, really big, we're not expecting our error to be small. But for h and k getting close to 0, we need our error to get close to 0 for it to, in fact, be differentiable. And what we're going to do is we divide our error by the distance that h and k are from my original, or sorry, we divide it by the square root of h squared plus k squared, because that's exactly the distance that I've gone from my original point. And that this expression creates a relative error. In other words, it thinks about how big my error is in relation to how far I've gone away from my original point. And provided that this approaches 0 as h and k approach 0, or written in limit notation here, then we say that the function is differentiable on the region R. So let's look at an example of that. It says in this problem, consider the function x to the 1/3, y to the 1/3. Show that the partial derivatives exist, but f is not differentiable. Okay, well, for the partial derivatives to exist, let's look at f of x uh, at the point x comma 0. And I'm looking at this partial derivative at x comma 0 because we're looking when a fixed value of y, which is 0. So this equals, using my limit definition of derivative, this would be the limit as as h approaches 0 of well, I'm at the point 0, so 0 plus h to the 1/3 times 0 to the 1/3. So again, this is my y value, which is at 0. Here I'm looking at my x point being 0 plus h, and then subtracting it from 0 to the 1/3 times 0 to the 1/3. So this is just a limit definition of derivatives. I'm looking at the point 0 plus h 0 and the point 0, 0. So I'm looking at how my function changes as I change h, and this is all over h. And this equals, well, when the numerator clearly is just 0. So this is the limit as h approaches 0 of 0 over h. So as h is getting close to 0, the numerator is already 0. So this is going to equal 0. So that's my partial derivative with respect to x at the point 0 comma 0. And the same proof is going to be true for y. We can go ahead and do it anyway. So we have f partial y at 0 comma y, where this is getting close to 0. So again, we're going to look at the points 0 comma 0 plus k and 0 comma 0. So this is going to equal the limit as k approaches 0 of 0 to the 1/3 times 0 plus k to the 1/3 minus 0 to the 1/3, 0 to the 1/3, all over k. And similarly to the last problem, this equals the limit as k approaches 0 of 0 over k, which is just 0. So the partial derivatives exist at this value. So that would suggest, that might suggest, oh, if the partial derivatives exist, then it is in fact differentiable. But that's not the case. So let's look at why. Remember that our error right here, our error or rather our relative error must approach 0 as h and k approach 0. So we have the limit as h approaches 0 and k approach 0 of my error. Well, what's my error? My error is going to be k to the 1/3, h to the 1/3. And that's going to be minus 0. The reason it's minus 0 is because my linear approximation, because my partials are both 0, and because at 0, My function is 0. My linear approximation is just 0 everywhere around the point 0, 0. So and then we divide this by my relative error, sorry, by my distance, which is h squared plus k squared. Okay, well, the trick here to solve this is since h and k are both approaching 0, let's let h equal k so that we can simplify this a little bit. And then we get the limit as h approaches 0 and k approaches 0, but I'm just going to have it all in terms of h. Of h to the 1/3 times h to the 1/3 all over 2h squared. And if we simplify this, and let's move this over to another page so that we can see it a little bit better. So if we simplify this a little bit further, this equals the limit as h approaches 0 of h to the 2/3, simplifying the numerator, over h root 2, so pulling that h squared out, further simplifying it, we get h to the 1/3 root 2. And what we see is since we have h in the denominator here, as h gets close to 0, this is actually going to get bigger. So this limit does not equal 0. So the fact that our relative error does not approach 0 implies, so therefore, our function is not differentiable. It's not differentiable because our linear approximation doesn't do at all a very good job. It doesn't do a good job at all of approximating the real function. Therefore, it's not differentiable. Okay, so let's think about one other term or topic, which is continuity. So we have a little bit of definitions here. It says if a function is differentiable at a point, then it is continuous there. So as long as we can prove differentiability, we can prove continuity. And once again, having both partial derivatives at a point does not guarantee that a function is continuous there. And that we can see from that last example, because if a partial derivative, you could have two partial derivatives, but the function may not be differentiable. Okay, so then we've got a theorem. It says if the partial derivatives of a function exist and are continuous, so as long as the partial derivatives exist and are continuous on a small disk centered at the point AB, then f is differentiable. So this is an important theorem that's saying that we can prove continuity if the partials exist and are continuous right around the point of concern. So using that, let's show that this function is differentiable everywhere in its domain. So first of all, its domain is such that x squared plus y squared must be greater than 0. And we know that because ln of something, the domain of whatever's inside the ln must be greater than 0. So we have f partial x is going to equal, well, the derivative of ln, you put everything over the denominator, and then the derivative of the inside is 2x. And since my domain is that x squared plus y squared is greater than 0, we know that the denominator will never be 0. And this function is going to be continuous everywhere, because there's no points of discontinuity since my denominator can't be 0. And f partial y, very similar, is going to be this. And both are defined and continuous provided that x and y aren't 0, or x squared plus y squared equals 0. But that's part of our domain. So therefore, this shows that our function is differentiable everywhere because the partials exist and they are continuous. So this was a short video that concludes our topic of differentiability of three-dimensional functions. It was a formal look at whether a formal look at how to determine whether functions are differentiable and continuous. Thank you for watching.